Lecture 3-3, Chemical Mechanisms and Catalysis. An overall balanced chemical equation does not indicate the molecular process that brings about the reaction. That is, it really doesn't indicate how the reaction occurs. For a generic reaction that occurs in two steps, step one would be A plus B makes C, and then C plus B makes D, with an overall net reaction of A plus 2B makes D. The sequence of steps that gives this overall reaction is known as the reaction mechanism. Compound C, the product of reaction 1, is called an intermediate because it also appears as a reactant in step 2, but is not a part of the overall reaction. Whenever we add everything up, it basically cancels out. Well, let's look at an actual reaction. If we take two nitrogen monoxides and put them together, we get dinitrogen dioxide, which is an intermediate. That intermediate is used up by reacting with oxygen in the second step to make two nitrogen dioxides, with the overall mechanism being two nitrogen monoxides plus oxygen to make two nitrogen dioxides. An elementary reaction is one that occurs in a single collision of reactant molecules. Each step in the reaction mechanism has to be an elementary reaction. The number of reactant molecules involved in an elementary reaction determine the molecularity of the reaction. If there's only one reactant molecule, it is unimolecular. If there are two reactant molecules, it is bimolecular. And if there are three, it is termolecular. Thus, the molecularity, the rate law, and the overall order for elementary reactions are related to the stoichiometry of the elementary step, but not related necessarily to the stoichiometry of the overall reaction. In this reaction, A goes to B is an elementary reaction that is unimolecular and follows first order kinetics and has a rate law of rate equals rate constant times the concentration of A. In the previous example, two nitrogen monoxides react to make dinitrogen dioxide. This elementary reaction is bimolecular and follows second order kinetics and has a rate law of rate equals K times the concentration of nitrogen monoxide squared. The slow step in a sequence of elementary steps that make up a reaction mechanism is called the rate determining step. The rate law for the reaction is that which is given for the rate determining step. The proposed mechanism must satisfy the following requirements. Summing the elementary reactions must result in the overall reaction, and the rate determining or the slow step must have the same rate law as determined experimentally. So, if we want to create a reaction mechanism for the reaction below, we are given the following. H2 plus 2 iodine monochloride makes 2 HCl plus I2, and the rate is given as rate equals K, the reaction constant, times hydrogen times ICl. The slow step has to be H2 plus ICl because the rate law says so. The rate law says that there has to be a hydrogen molecule and an iodine monochloride molecule. The products have to somehow relate to the products that we're going to get in the reaction. They all don't have to, because one of them may be, as we saw before, an intermediate that will be removed in a later step. But since we're producing HCl and iodine, then we have to produce in that slow step either HCl or iodine and another product. So what we see here is that if we split the hydrogen and put it with a chlorine and an iodine, then we get one HCl. In step 2, the hydrogen iodide reacts with the ICl to form another HCl, because we need 2 of them in the reaction mechanism, in the overall reaction, plus I2, which is also part of the overall reaction. So putting all that together and summing everything, we have H2, which is from the slow step, plus 2 ICl, 1 each from step 1 and step 2, 2 HCl's, 1 each from step 1 and step 2, and iodine, which is a product of step 2. And as we can see, the hydrogen iodide appears both in a reactant and in a product, and as a result, it is an intermediate. In some cases, the first step is not a slow step. Instead, it is a fast step that quickly reaches equilibrium, because the product of step 1 cannot be used as quickly as it's made. So part of the reverse reaction occurs. From the slow step, we get rate equals the rate constant times NOCl2 times nitrogen monoxide, NO. However, if we look at it above, NOCl2 is an intermediate and should not show in the experimentally derived rate law. The NOCl produced in the fast step and used in the slow step, so the concentration of the NOCl builds up as the fast step begins. And eventually it will start to run in reverse, so the NOCl2 will start to break down back into nitrogen monoxide and chlorine, going this way. When we have that occur, we can use the fact that this is a reversible reaction and get rid of the NOCl2 in the rate law, as we will shortly see. So this is an equilibrium step, and a dynamic equilibrium is established. The forward reaction is K1 times the concentration of NO times the concentration of Cl2 here. The reverse rate, we give the rate constant a -1 to show that it's the reverse of the first reaction, has a rate constant K of -1 times the concentration of NOCl2. But eventually these two rates become equal to each other, and we can say that the forward rate equals the reverse rate. So K1 NOCl2 equals K -1 NOCl2. And then by rearrangement that is, the concentration of NOCl2 equals K1 times the concentration of NO times the concentration of Cl2 divided by K -1. And what we do with the reaction constants, and now they're both constant, we can take the K1 divided by the K negative 1 and call that a new reaction constant, which we will shortly see. Substituting the previous equation for NOCl2 into the rate law for the slow step, the rate law becomes K2 times K1 times concentration of nitrogen monoxide squared times the concentration of chlorine divided by K negative 1. We're just going to simply combine all the rate constants together, seeing how they're all constant. And what we get is the following rate law, and that is the rate equals KNO squared times the concentration of chlorine, which appears to be a termolecular reaction. But this termolecular reaction actually occurred in 2 steps, with one of the steps being slower than the previous step. The following reaction basically occurs in 3 steps, and the slow step is bimolecular. Determine a reaction mechanism. The overall rate law is rate constant times the concentration of hydrogen times the concentration of nitrogen monoxide squared. Seeing how the slow step is bimolecular and the rate law is termolecular, that tells us that the slow step is either the second or the third step. So what we have to do is come up with a reaction mechanism that will help us determine what is going on in this reaction. So thinking about it, for the slow step, we have a couple of choices. Hydrogen can't react with itself because it'll just form more hydrogen. But we could have a hydrogen react with a nitrogen monoxide, or we could have 2 nitrogen monoxides react together, or the slow step is something unknown, an intermediate, plus either hydrogen or an intermediate plus NO. Seeing how this is a termolecular, we are going to suppose that we have an intermediate from a previous step, so we won't look at H2 plus NO or 2NO in the reaction. We're going to form an intermediate and either react it with H2 or react it with NO. So let's suppose that the second step is the slow step in this reaction mechanism. So we're going to have an intermediate plus either nitrogen monoxide or H2. So first let's experiment with it being hydrogen. And again, if we do that, we're going to have a product that has another intermediate for step 3, and then also one of our products. Well, one product that we might get if we do hydrogen is we're going to make an H2O in that, which means that our intermediate must supply us with an oxygen, and we could simply do that by putting a single oxygen there as a possibility. So going back up to reaction 1, we have to have an oxygen as a product. So as a reactant, or reactants in this process, we could either have a single nitrogen monoxide falling apart into a nitrogen and an oxygen, and then we use the oxygen with the hydrogen to make H2O. So now we've gotten rid of the oxygen, and we're left with a hydrogen that has to be used and a nitrogen monoxide that has to be used and a nitrogen that has to be used. And as you can see, this gets to be a little bit complex because there are 3 reactants in the third step, and that's generally not the case. And you're asking, well, why would I show you a bad mechanism? Because with mechanisms, sometimes you have to experiment with them, and it's a process of learning and eliminating possibilities. So let's do this. Let's do a slow step that has an intermediate plus NO instead of H2. And given that, we're going to have 2 products, most likely. One of them is an intermediate that will go into step 3, and one of the products. So generally an intermediate is not one of our reactants, so we couldn't put an H2 plus NO as the slow step in the second step. So maybe we think of other possibilities. One is we could just simply put a nitrogen in there. Another is we could put a single hydrogen in there. Or we could put a single oxygen in there. But the one that probably makes the most sense is to put another nitrogen in there, because it will help give us one of the products, which is the diatomic nitrogen. So we'll put a nitrogen here, and it will make N2 plus O. And seeing that O at the end makes me think, well, maybe that oxygen will quickly react with some hydrogen to make water, because we need 2 of those. And that will get rid of this oxygen as an intermediate. But it also will tell me this, that one of the products up here is H2O, and the other product is nitrogen, because I need one more water molecule, and I need to make a single nitrogen. And I've already used up one H2, so I'm going to put the second H2 up there. I've used one NO, so I'm going to put another NO up there. And this looks good. H2 will pick up the oxygen off the nitrogen monoxide, leave a single nitrogen that then will react with the nitrogen and oxygen to produce the diatomic nitrogen and a single oxygen, which reacts with hydrogen to give H2O. The question then becomes, will this fit our rate law? And currently, we have, if this is the slow step, rate equals K2 times N times NO And from the first step, which is at equilibrium, we have K1 concentration of H2, concentration of NO, equals K minus 1, I'm going to run out of space, concentration of H2O, times the concentration of N. And if we substitute after rearrangement of the nitrogen back into here, we're going to have basically this. Let me make myself a little bit of space over here. Get rid of that. And we end up with the concentration of nitrogen equals K1 over K minus 1 times the concentration of hydrogen times the concentration of NO divided by the concentration of H2O. But that leaves us with a problem, and that is, if I substitute all of this into the rate law, we end up with a hydrogen in the denominator, and that's not what we want. So, as you can see, creating a reaction mechanism can be a little bit difficult. So, let's talk about one of the other aspects of working with rate laws. Since there is no reaction concentration in the denominator, that tells us in the first step, if we're going to have the second step be the slow step, in the first step, we're going to have a single product and none other. In step 2, we're going to have to use that single product and react it with one of our reactants to make other products in a slow step. And then in the third step, we're going to have to use up an intermediate that is produced here to finish the reaction. Well, let's look at this. Let's start out with an H2 plus an NO. The reason why I've chosen those is because this has an H2 and it has an NO. I could have chosen NO reacting with itself. That's a possibility. And I'm going to have this produce a single molecule, H2NO. That intermediate, H2NO, then reacts with another NO, and produces H2O plus N2 plus a single oxygen atom as our intermediate. I could have chosen another H2, but then we end up with an unusual H2N, and we're not making a lot of our own products. This helps us make more of our products that we're looking for. So we've already got one hydrogen, we've got the nitrogen, and now in the last step we take the oxygen, react it with a hydrogen to make the second H2O. So what about the mechanism? Well, I'm going to erase the third step because it won't be involved in the reaction, pardon me, not reaction to rate law. It just finishes up the reaction. And so the rate equals K2 times the concentration of this H2NO times the concentration of NO. And for the first reaction, which is reversible, we have K1, concentration of H2, times the concentration of NO equals K1 times the concentration of H2NO. So I'm going to move the K -1 over here. So now I can substitute this H2 and the NO in the rate law, which is now K2, K1 over K -1 times the concentration of H2 and the concentration of NO squared. Writing reaction mechanisms takes practice and patience, and you need to do quite a few to realize the little tricks that come into it. So realize that anything that is termolecular or more probably has a slow step that is either the second or the third step, and others that are unimolecular or bimolecular probably have a slow first step. And you have to use a little bit of creativity to determine what those steps are and what the reactants are and what the products are. Just a recommendation, products of elementary steps should lead you to the products you need in the overall reaction. Catalysts. Catalysts are chemical species that, when added to a reaction, increase the rate without being consumed. A catalyst may form an intermediate in one step of a reaction but is regenerated in a subsequent step. The degradation of hydrogen peroxide can be increased by the addition of iodide, and the mechanism is follows. H2O2, hydrogen peroxide plus iodide makes H2O plus IO minus, which is hypoiodite. And the hypoiodite plus another peroxide makes H2O plus O2 plus iodide. So note here that the iodide is regenerated in step 2. It is a reactant in step 1, a product in step 2, which is the difference between an intermediate, and that is an intermediate is a product in a step and then consumed in a later step. Catalysts speed up reactions by giving more energetically favorable elementary steps. This lowers the activation energy and therefore speeds up the reaction. In some cases, what a catalyst will do, in addition to lowering it, is it provides another pathway. And so what you may see is something that looks like a camel. It goes up and a little up and then down. So you end up with a couple of barriers to get over, but those barriers are low enough that they don't get as big as the overall activation energy. Types of catalysts. There are homogeneous catalysts, which are in the same phase with the reactant molecules. That is, if it's an aqueous reaction, they are aqueous. In the reaction of salicylic acid with methanol to form methyl salicylate, which is the smell of wintergreen, the addition of sulfuric acid makes this reaction occur, and the sulfuric acid is in the same phase as the salicylic acid and the methanol. Heterogeneous catalysts are in a different phase than reactant molecules. For example, in organic chemistry, the hydrogenation of alkenes can occur by absorbing hydrogen onto a solid to facilitate the addition of H2 to a carbon-carbon bond, as shown in these pictures on the right. Enzymes are biologically manufactured catalysts which provide an alternative pathway by bringing either the substrate in to break it up or to bring two substrates in together to make a new product. So they can either make something new or they can break something apart. Since they are generally in the same phase with the substrate molecules, they are considered homogeneous catalysts. Back at the previous slide, the fast step is shown by a lower activation energy than the slow step, which has a higher activation energy. And finally, the mathematical treatment of enzyme kinetics is slightly different. You have the enzyme plus the substrate makes the enzyme-substrate complex, and that's the fast step. And the enzyme-substrate complex then produces the enzyme back, which is the catalyst, and the protein, or the product. The rate equals the change of the product with time, which equals the rate constant times the enzyme-substrate complex. When the enzyme-substrate complex is saturated with substrate, that is, there's more substrate than there is enzyme, the reaction rate depends on only how fast the enzyme-substrate complex then breaks down. And at this point, it becomes a zeroth order reaction. A reaction of this type is like when the liver breaks down ethanol. At first, a little bit of ethanol in the bloodstream, and there's a slow buildup, but at some point, the enzyme that breaks down the alcohol gets saturated by alcohol in the bloodstream, and so the blood alcohol level continues to rise, but the amount of alcohol that is processed through the liver remains at a steady state.